In geometry, one important application of proportionality involves similar triangles. Two triangles are called similar if they have the same shape. Example 4. Which of the following pairs of triangles are similar? Although the triangles on the left are different sizes, they appear to have the same shape, while the triangles on the right are different sizes and different shapes. So, although we can't be sure without taking measurements, the pair of triangles on the left appear to be similar. The properties of similar triangles include the following. 1. Triangles are similar if all corresponding angles have the same measure. Therefore, to truly know if two triangles are similar, without just eyeballing their shape, we might measure each angle and show that corresponding angles have the same measure. Property 2. Actually, if even 2 of the 3 of the corresponding angles have the same measure, the triangles are similar. This is because the sum of the measure of the angles in a triangle is always 180 degrees. Thus, if you know the measure of 2 angles in any triangle, you could find the measure of the third by taking the sum of the 2 that you already know and subtracting from 180 degrees. Thus, if you have 2 pairs of corresponding angles that are the same measure, you really have 3 pairs of corresponding angles that are the same measure. Hence, the triangles are similar. Finally, property 3 states, for similar triangles, ratios of corresponding sides are the same. According to our alternative definition of proportionality, this means the lengths of corresponding sides are proportional. Example 5. The two triangles below are similar. Find the lengths of their missing sides. Usually in mathematics and in life, there's more than one way to solve a problem. One method of finding the missing side lengths involves using the fact that for similar triangles, the ratio of corresponding sides are the same. This means 12 over 3 must equal 16 over little c. Now that we have set up an equation, we can solve this equation to find c. Since this equation is of the form fraction equals fraction, we can cross-multiply to get rid of the fractions. We get 12c equals 16 times 3, which is 48. Now let's divide both sides by 12. Dividing by 12 undoes the multiplication by 12 on the left. On the right, 48 divided by 12 equals 4. So little c equals 4 units. We could set up a similar equation to find big B. But just for practice, let's use another method. Since the triangles are similar, the lengths of corresponding sides are proportional. The definition of proportionality tells us that the length of a side on the big triangle must equal a constant times the length of the corresponding side on the small triangle. If we can find that constant, we should be able to find the length of big B. Let's use the fact that we know the length of both big A and little a to determine this constant. Since big A equals 12 and little a equals 3, we have 12 equals the constant times 3. If we divide both sides by 3, we get the constant equals 4. The fact that the constant of proportionality is 4 means the length of a side on the big triangle is always 4 times the length of its corresponding side on the smaller triangle. That is, 4 times little a equals big A, 4 times little c equals big C, and 4 times little b equals big B. Since we have little b equals 2 units, we know that big B must equal 4 times 2, or 8 units. Example 6. Suppose we find that a tall building casts a shadow of length 25 feet. At the same time, a 6-foot-tall man casts a shadow 2 feet long. How tall is the building? To answer a question like this, it's helpful to draw a picture. This picture shows the height of the building and the height of the man, as well as the length of their shadows. Note, because these measurements were taken at the same time of day, and we are assuming the building and the man are relatively close to one another, we can assume the rays are parallel. The sun's rays create equal angle measures at the top of the building and at the top of the man. Because of this, we have that the triangles created by the building and its shadow and the man and his shadow are similar because 2 and consequently 3 angle measures are the same. Moreover, since the triangles are similar, we have that the ratios of corresponding sides are the same and the lengths of corresponding sides are proportional. Since the ratio of corresponding sides are the same, the height of the building over the height of the man is equal to the shadow cast by the building over the shadow cast by the man. That is, the height of the building divided by 6 feet equals 25 feet divided by 2 feet. Since all the units are the same, we can go ahead and solve this equation by cross-multiplying. We get 2 times the height of the building equals 25 times 6. That is, 2 times the height of the building equals 150. If I divide both sides by 2, I get the height of the building equals 75. And since our unit is feet, this means the height of the building is 75 feet. Of course, there are other methods we might have used to solve this problem. Since the triangles are similar, we know that corresponding sides are proportional. So we might have solved this problem by finding the constant of proportionality. Since we have to multiply the length of the smaller shadow by 12.5 to get the length of the larger shadow, 12.5 is our constant of proportionality. Knowing that, we could have found the height of the building by multiplying the height of the man by 12.5. Note that 6 times 12.5 equals 75, so our answer would have matched the answer we got using the original method.